We're now going to move to the next portion of the course where we're going to be introducing algorithms and how we would analyze algorithms. Before we start looking at different data structures and algorithms, we first need to understand more about what algorithms actually are and how we can compare algorithms. We asked before, is one algorithm better than the other? And we said yes, it is possible, but we need to see how do we determine that one algorithm is better than the other. So first of all, what is an algorithm? I think we mentioned before that it's just simply a set of steps, but specifically we can think of it as a clearly specified set of simple instructions to solve a problem. It's not enough just to write a simple list of instructions to do something. It has to be clear, it has to be precise, it has to be something where if I give it to someone else who knows very little about the problem, they can follow the steps and solve the problem without any major issues. That's an algorithm. And I will mention that writing algorithms is not an easy task. You'll find out more about this in other classes. It's not easy to come up with algorithms, but it's a very important part of writing programs, which is why we are mentioning it in here. And what we're going to see later on is when we work with data structures, there are different procedures for handling different operations for the data structures. We need to understand those algorithms before we can move on with those data structures. Now, let's say we have an algorithm and know that it's correct. That's the first step, to make sure that we have an algorithm that actually works. But once we have that, we need to make sure that it's a useful algorithm. And the way we do that is we determine how much resources does the algorithm require. Now, when we talk about resources, we usually refer to the amount of time it takes to run the algorithm and how much time, or I should say how much space, is needed to store the data. So, for example, if we have an algorithm that works, but it takes years to run, well, that's not going to be a very good algorithm. Also, if we have an algorithm that requires terabytes of data, we really can't use that algorithm either. Now, when we say time, we don't mean clock time. We don't mean take a stopwatch and start it as soon as the program starts and then stop it when the program is done. And this is because the time it takes to run a program is going to vary by machine. I could take the same program and put it on 100 different machines, and it's very unlikely that I'm going to find two machines that run the program at the exact same time. Depending on the type of architecture, CPU, RAM that you have, they are going to vary. So we don't look at this in terms of a clock time or an execution time. Instead, whenever we refer to the time of an algorithm, we're talking about the number of steps it takes with respect to the size of the input. So if we're given some input size, how much time does it take? Does it take the same amount of size? Does it take less? Does it take more? But we look at it with respect to the input size. And what we're going to do is we're going to let n, or at least capital N, be this size of input. So given an input of size n, how many steps, how much time, or additional time I should say, does it take to complete the algorithm? Now, when we say space, we don't mean physical hard drive or USB drive space. We don't talk about in terms of the number of gigabytes or megabytes or terabytes or anything like that. What we mean is the additional space besides the size of the input. So if we're given an input of size n, so we'll use n here for both the variable that represents the time and the space, how much additional space on top of the input size do we need to complete the algorithm? Do we need the same amount of space? Do we need a bunch more space? Do we need very little space? So we're going to look at how much additional space do we need along with storing the input size. We're next going to take a look at some of the notation that we would use in order to compare the algorithms. Let's suppose we have two different algorithms that correctly solve the same problem. The question we want to ask is one algorithm better than the other? And we've already mentioned that the answer is yes. And it comes down to how we use the resources. How much time do both algorithms use? How much space do both algorithms use? So if we can determine the resource usage of both algorithms, we can compare the two and decide, is one better than the other? Is one faster than the other? Is one more memory efficient than the other? So it really comes down to the resource usage. But if we're going to do that, we need to decide, how do we notate that? We need to find some way to denote the resource usage. So if I say it takes so much time, how do I do that with respect to n? There are several different notations we can use for comparing algorithms. The first one we're going to talk about is what's called the big O notation. This one is the most common among all the different notations we're going to be discussing. Let me give you the format first, and then I'll explain how it works. So it looks something like this. We have a capital O, and then a pair of parentheses around it. And then inside of it, we have this f of n, which is a function of n right here. Now this could be n, it could be n squared, it could be 1/2 n, 2n, but some function with respect to n. So all we're doing here is we have a capital O right outside the parentheses right here. Then we have the parentheses and then some function of n. That's the notation. Now how does this work? Well, let's suppose we have t of n, and this is a function that represents the actual time of the algorithm with respect to the input size n. And here, just as a reminder, when we talk about time, we're talking about the number of steps, not the actual clock or execution time. But let's just say t of n is the actual time the algorithm takes. We say that t of n is equal to big O of fn if we have two positive constants, c and n naught, where t of n is less than or equal to c times f of n whenever n is greater than or equal to n naught. So what does that definition mean? It seems like there's a lot of math. And by the way, I should mention there's going to be a good amount of math involved here. But let me try to explain it from a high level perspective. So let's say f of n is some growth rate function. So as n increases, we have a function that's also increasing in some approach. And let's suppose we're at some point, some value of n, which we call n naught. Now, there could be values beforehand, there could be some values afterwards, but we have some point which we're going to call n naught or n0. From that point onward, or in other words, when n is greater than or equal to n naught, remember that this part right here is part of our definition, if t of n is always bounded above by some constant multiple of f of n. So that's where we said if t of n is less than or equal to c times f of n. So we're saying here, if t of n is always bounded above by some constant multiple of f of n. Now that constant multiple could be 1, but it's some constant multiple, then we say that t of n is equal to O of f of n. So what we're saying here is we want to know the upper bound on our growth rate as we increase the value of n. So we're just saying if the value of n increases, what's the upper bound of our growth rate? How bad or how large can it get? Let's give an example here of using this big O notation and how it actually works. Let's say we want to compare two growth rates, where one of them is 1000 n and the other one is n squared. So clearly, when n is really small, 1000 n is going to be larger than n squared. So think of it like this way. For example, when n is 1, well, 1000 is going to be greater than 1, because 1 squared is 1. So when n is really small, 1000 n is clearly greater than n squared. But we know that n squared is going to grow at a faster rate than 1000 n as we increase n. We might not see it right away, but eventually when n becomes large enough, n squared is going to become greater than 1000 n. And if we want to be specific about it, this happens when n becomes 1000. So what we see here is we're going to let n naught be 1000. So from this point onward, so for any value of n that is greater than or equal to 1000, 1000 n is going to be less than or equal to c times n squared. Here, we'll let c equal 1, because we just said some constant multiple of our function of n here. So we can let that be 1. That's perfectly fine. And what this means is if we apply this to our definition of the big O notation, 1000 n is equal to O of n squared. So what we're basically saying here is that the growth rate of t of n, we're talking about a general statement here. In general, the growth rate of t of n is less than or equal to the growth rate of f of n. That's all we're doing here. We're just comparing the growth rates. The growth rate of the first function is less than or equal to the growth rate of the second function. And if that's true, then we can use the big O notation. So big O notation is just simply saying the growth rate of the first function, t of n, is less than or equal to the growth rate of what's inside the parentheses of the big O notation.